Howdy. Howdy. All right. So, um, hopefully this doesn't buffer all over the place. I really need to stop doing streams from my house, or rather, streams from this computer. So, but I'm bored and irritated, and that always, always amounts to a good time. So let's crack one open. Sadly, this is not beer. This is actually water. I am trying to be healthy for reasons that I still don't quite understand. But there you go. So, there are a couple things that I wanted to talk about today. Let me scooch back over here. So I made a video, mainly a rant, about the celestial theodolite experiment being done over there by by the Aether Cosmology community, specifically Alan, Space Audits, and Shane St. Pierre. They are and also Dr. Heffron. Dr. Heffron, I believe, is actually the one doing most of the heavy lifting in terms of the mathematics and doing the running through the procedure and all that kind of good stuff. But as I admitted in the previous video, the specifics of this the specifics of this experiment are unknown to me because as I've stated now repeatedly to Alan, because he went into my comment section of that video, that his initial premise that you could ignore the refraction of starlight going through the atmosphere prior to hitting the mountain, that premise is flawed. You cannot ignore refraction in this experiment. You cannot compare your results to something that neglects refraction in this case. It is simply a factor. It is a physical manifestation or physical property of the atmosphere. There is no trick that you can do that will change that fact. In your most recent post that I saw, you asked the question, what is the angle of a star which has been occluded, the refracted angle of a star that has been occluded by the mountain? And you seem to imply, and maybe I misunderstood, you seem to imply that if that angle is 0, then I understand the premise of the experiment. Well, that angle is not 0. The fact that it is occluded does not mean that that star no longer exists and that one can no longer take an angle to it. Let me rephrase. It doesn't mean that that star no longer exists, and does not mean that an angle exists from a horizon to that star. You cannot take one, you cannot measure one simply because the mountain blocks the view. However, let's imagine you have technology where you can look at wavelengths that pass through the mountain. Possibly radio. I'm not entirely certain whether or not radio can go through a mountain, but let's say you can use wavelengths of light that pass through mountains. We have examples of wavelengths passing through solid objects all over the place. Wi-Fi, for example. If light could not pass through a solid object, then Wi-Fi would be pretty limiting. So, if you were able to observe the star in a wavelength such that the mountain was transparent, then you could take an angle to it. This is not something that can be ignored or done away with. And you can call me, you can claim that I am misrepresenting you all you want. You can claim that I'm not being academic all you want. It does irritate me because it's not honest, But you can do it all you want. It does not change the fact that the atmosphere, which is present, always refracts light. Now, if you want a more concise explanation of this with diagrams, a very nifty diagram, to be honest with you, I would check out I Can Science That video and go beyond the intro. From my understanding, or the salient point to this is somewhere near the middle of the video, where he shows the situation as it is physically, and he shows what it is optically. Basically, the mountain height is also affected by refraction. The mountain is actually appears higher up than it actually is in reality. And so in that diagram, he demonstrates the physical, or the alignment that you are seeing to the alignment that's actually happening. It's rather nifty. But I am going to be that guy for a moment, because this is relevant to this. And again, this is a part of the argument that I don't think has been addressed yet, is that another reason why I have never really talked about refraction, either in this context or in the context of seeing too far, is because this is a complex phenomenon. And as an astronomer, I'd go out of my way to avoid it. One of the reasons why we use a technique called differential photometry is to avoid all of the complications that occur because of refraction of starlight through the Earth's atmosphere. In order to deal with it properly, you have to do this thing called absolute photometry, which is a pain in the nuts and can really only be done on perfectly photometric nights. That means that the seeing is excellent, that the transparency of the atmosphere at that point is excellent. Basically, there are no stars, there is relatively no humidity. You have to have optimal conditions in order to do this. Additionally, you cannot have any sort of light gradient due to localized pockets of light pollution. What I'm trying to say is that I have only successfully, and it was marginal, I was only able to successfully do this once. And never again. I've tried a couple of times, failed miserably. Because again, this is a process which requires very specific conditions in order to do it properly. And this method is what accounts, or what takes care of, or describes rather, the effects that refraction has on observations. Specifically in terms of magnitude and color. But there's another aspect of this that is that I don't deal with, because I do not do a branch of astronomy called astrometry, and that is the position of the star also changes. So in order to, how do I want to phrase this? When you are observing a star through the atmosphere as an astronomer, you understand that the light that you are seeing is dimmer than it is in actuality. It's redder than it is in actuality, and the star's position is not accurate to where it is in the actual sky. It's where it is its apparent location. I think in stellarium, when you look at the sun, if you were to click on the sun, you have the coordinates of the sun, and then you have the coordinates of the apparent sun. It's there because of refraction. And I feel like the meme, the gravity meme, I don't know, doesn't get played all that often anymore. So OG flat Earth debunkers might know it. It's a dude who looks kind of like me at the moment, who says, "Gravity! Gravity! Haven't you heard of fucking gravity?" I'm getting to the point of trying to do a meme where it's refraction! Refraction! Have you never heard of fucking refraction? I'm getting tired of saying the word. So, to my point, and I put this in a comment section somewhere. Oh, howdy, Judy. Howdy, Lisa. Is that astronomers rarely, if ever, observe anything above 2 air masses. Really, you never want, if you want good data, you really don't want to observe above, below or above 1.5 air mass. Now, what do I mean by air mass? Air mass is a term that we use to quantify how much of the atmosphere we're looking through. The larger the air mass, the larger the refraction is that's going to take place. So air mass of 1, by definition, is straight overhead. You are looking through the shortest amount of atmosphere that you possibly can. And then it is a secant function as you go towards the horizon. So if the object is lower than 45 degrees, there's no point to look at it unless you just want to see pretty colors. Because the data is going to be of such poor quality as to not be, at best, it won't help you solve or answer the question you're trying to answer. At worst, it's going to be of so poor quality that it may actually cause you to misinterpret the data because it is so bad. So, my point is, as an astronomer, there's no way in hell I'm going to be looking at anything at the horizon because the refraction is so egregious. This is also seen with the sun, and this is something that we've talked that debunkers have talked about with flat Earth, with the sun on the horizon. There is something known as differential refraction. This is because, and this is, I say this as an example of how extreme or how big of an issue this is. Differential refraction means that you have an extended body, and so therefore the top of the body and the bottom of that body are going to be viewed through different amounts of air mass, which means the amount of refraction that the top of the sun experiences with respect to the bottom of the sun is going to be less. What that ultimately means is that the sun, which is observable, this is an observable reality, is that the sun gets squashed by enough that you can actually perceive this. This is not a small effect. You can also see this effect with the moon, although it's most notable with the sun because the sun is, well, the sun isn't larger. I don't know. I just haven't really seen a good moonshot where it's squished. Only suns. Mainly because the sun is more photogenic. I don't know. You see the... Oh, you was in Hawaii, Lisa? Kalala Observatory. I have to say that I'm going to lose some of my astronomer street cred and say that I don't know where that is. I am not familiar with that observatory. The observatory I'm most familiar with, obviously, is Mauna Kea. So yeah. Wait a minute, Maui. Is that where Pan-STARRS is? Anyway, I'm getting off track. So you've got that. But there's another aspect of this that no one, as far as I know, has talked about. And I don't know if it's been accounted for in the data. And perhaps this is also one of the sources of error in the data. Well, this is one of the sources of error in the data that you have to take into account, which is that refraction is time dependent. I actually watched one on TikTok today. I was scrolling through TikTok and I saw, an out of focus image of a star, and the guy had done some, I don't know, I think he was trying to be artsy. I don't think he was being a flat earther or anything of that nature, because he had this like reverb with the sound and there was this echo. It just seemed like he was trying to be really artsy for whatever reason. But it was it was one of the washed out, looks like you're looking at something through water. It was very pretty. It was bouncing all over the place. The reason why it looks that way, the reason why an out of focus star looks the way it does, or planet, where it looks kind of like a ring. There's kind of a dark spot in the center of it. Kind of looks like a ring. It looks almost filamentary. There are a number of different colors. You can see blues and reds and greens and all sorts of things with that. That is because not only is refraction occurring, refraction is wavelength dependent, but it is also time dependent. The atmosphere is not some static dome where the air does not move, change temperature, or composition. All of these affect the amount of refraction that light passing through it experiences. So when you are doing your timing of this, the parent location of the star, the parent angle, the angle measured to the star, although from my understanding, you're not measuring that, you're measuring the timing. But that's going to change. The timing of the occultation is going to change because of its relative change in position over time. Now, I could be adding a complication in here that is very minor. I will freely admit that. Like, I don't have a good sense of how much it's going to affect the timing of the occultation. We are talking about an effect that's on the order of arc minutes. So depending on the speed of the star at that point, it could be that the time component of this, or the time dependency of this, is negligible. Can be. However, I would like someone to talk about it. I would like someone to actually notice or note that not only is refraction present, but it is also time variable, and that's also going to affect the process. Which leads me again back to why I've really not paid attention to this experiment, is because it is poorly planned. It does not take into account all of the variables involved, all of the effects to the observations involved. And if I were to come up with a way to determine the shape of the Earth, this would be on the bottom of the list of ways that I would do this. It would be even lower than laser ranging over a body of water. It's not. It's very novel. I will grant this. It is an extremely novel way to attempt to determine the shape of the Earth. However, because of how messy and how difficult it is to quantitatively describe the amount of refraction that is occurring at that time, at that angle, you're going to be dealing with a huge amount of error. A huge amount of error in your data that I don't think is going to be able to give you the answer you're looking for. I don't think that type of experiment, or I would be very surprised if this experiment can support any shape of the Earth, or rather at least flat or globe, because of the fact that the refraction is so variable at that point. The apparent position is going to change, and it's, like I said, it's going to change as a function of time, and it's going to change significantly at those altitudes. So yeah, that's basically what I want to talk about in terms of the celestial theodolite, and I think that'll be the last thing I talk about, and last time that I talk about the celestial theodolite, until that experiment is revised such that refraction is accounted for completely. Then looking into it is not worth my time, because anything that follows after that is not going to be worth a damn. It's not going to be relevant. I mean, yeah, that's basically where I want to go with that. It's kind of like I want to, and maybe it's just the times. I want to, bomb. I'm trying to be politically correct about this. I want to bomb the Irish. Fuck it. Because I heard that this dude named Garen Known, who lives in Mayo, is a racist. So I want to bomb his house. So, to me, this experiment is akin to attempting to bomb his house without accounting for air resistance. I mean, I can get there. I can get within the vicinity of, I think I could hit the island, but I sure as shit not going to hit his house. I might come close, but again, that would be ignoring something that is fairly vital to the given the precision of the required precision of this experiment. So yeah, unless the experiment actually addresses refraction, or they stop saying things like the refracted angle of the star goes to 0 when it is occulted. Until they stop saying things of that nature, I'm simply going to stop engaging. So that's where I'm at with that. Ooh, sorry, Luna. So what else am I going to bitch about? Let's bitch about Avi Loeb, because that seems to be the fun thing. And sadly, Clive is not here, because I was going to talk about aliens. Unfortunately, I'm going to be saying that 3i Atlas is not aliens. So, for those of you who might not be familiar with what 3i Atlas is, let me bring up a picture of it. Oh, this is the... Okay, never mind. So, here we go. Let's start off with this one. I want to do that. Yes. So, I can no longer see the comments. Let me do that. Hey, now I can see the comments. Avi the Grifter. I don't know. As I've mentioned before, Avi is, or as I've mentioned before, there is a notable tendency for older professors to become quacks. I don't know why. So, generally speaking, in my lived experience, in having been in, 5 departments, physics and astronomy departments at this point, it usually goes one of 3 ways. You have a professor who reaches the retirement status, and they retire with what I call a small r. They become a professor emeritus. Basically, they still have an office. They still count as a faculty line. Basically, because this person has retired with a small r, means that we cannot hire a replacement. We cannot hire someone else. When a faculty member usually leaves for whatever reason, that frees up the faculty line, and so we can hire an additional faculty member or a new faculty member. In this case, not so much. The professor no longer teaches classes. He no longer mentors students. He'll come into the office whenever he wants to, and that's basically it. 2, he will, or she, they will continue to do active research until they die in their office. These are professors who are extremely sharp and whose faculties do not seem to be impaired by this thing we call age. And so I've known a couple of these individuals, and I envy the living fuck out of them. I mean, these guys are just amazeballs. The way that they keep themselves active, they keep their minds active, and yeah, they just continually do active research. And they'll teach. So basically, they don't retire. And the third one is kind of a subset of the first one, is that you'll retire with a small arm. Like I said, you'll hang out, you'll do your thing, you'll come into the office or what have you, and you'll putsy around. You'll basically do what retired people do, I guess. Or you'll think, you know what? I've come up with an idea that no one else has ever come up with, and I am going to revolutionize something. Be it quantum mechanics, cosmology, exoplanet, extraterrestrial science. And you become a quack. You then start adopting ideas that are, shall we say, on the fringe. You reject any sort of legitimate criticism of those viewpoints. And you start making claims that you are, in fact, a person with special knowledge. Yeah. You become kind of a conspiracy theorist. That is where I think Avi is. And yes, I think part of it is being a grifter, because I think, well, again, this derails a little bit into, and let me do this. For those of you who are not aware, I'm responding to someone in chat. Real Cygnus referred to Avi as the grifter, and then they put in book sales. What I would say to that, and I've talked about this before, I've had conversations with, like in science, that is, what does it mean to grift? I think it takes more than just simply making money off of false ideas. To me, a grifter is someone who does not actually believe in what they are selling, and they are simply putting out these ideas in order to make money. And it's the belief part that is important to me. I don't believe that Avi is a grifter. I don't believe that Dr. Loeb is a grifter, because I do believe he believes in what he is selling, because he is and has been an arrogant prick, from my understanding, his entire life. And so this idea that he holds special knowledge is right in his wheelhouse. It's basically, true to form, I should say, with it. So I don't think he is a grifter. I truly think that he believes himself to be the new messiah of aliens, of UFOlogy. Oh, sorry, my cat's in my lap, and she's very annoyed that I'm not petting her and that I'm moving around. But she is making my legs very, very... It's very uncomfortable, but it's a cat, and so I'm kind of stuck. So thanks, Luna. So yeah, I don't think he's a grifter. I think that he honestly believes in what he's selling. So getting back to 3i Atlas. Now, you might be asking, what is 3i Atlas? What is the name? Well, 3 stands for third, I stands for interstellar, and Atlas stands for the mission that found it. As far as I know, it has yet to be given a proper name, as it were, like Oumuamua. I don't know if it will, but Atlas is an acronym for a survey mission that's looking for these types of objects, from my understanding. So that's why it's called 3i Atlas. Pay attention to the 3. I'm going to come back to that. This object is on a hyperbolic orbit. And you might be asking yourself, Professor Parks? Oh, no. Let me back that up. It's on a hyperbolic orbit. What that means is that the object is passing through our solar system and will leave and never come back. Now you might be asking yourself, how is that in orbit? You know, we say that the moon is in orbit around the Earth. It goes around and comes back again. The Earth is in orbit around the sun. It goes around and comes back again. Well, astronomers are often very, shall we say, fast and loose with certain terms. For example, metals. Anything that is not hydrogen or helium is classified as a metal to an astronomer. So yeah, oxygen is a metal to us. Orbit, to us, is basically defined as a geometric shape that an object, or a geometric path that an object traverses, where the sun is considered to be at one of the foci, or the center in the case of sun. So you have 4 different types of orbits. You have a circular orbit, you have an elliptical orbit, which I guess is technically a subsection of elliptical. You have parabolic, and then you have hyperbolic, which I guess you could think of hyperbolic as maybe being a subsection of hyperbolic. In essence, you have 2 types of what we call closed orbits or bound orbits, where an object will move in a path where the objects will come back around. It will stay in the localized area of the thing that it's moving around. If something is on a parabolic or hyperbolic trajectory, then no, it will pass by the object that is in its focus, and then it will continue on its merry way, never to be seen by that object ever again, unless something weird happens or some force acts upon it. Moving in the best circles. Doesn't change the fact that Lisa says it doesn't change the fact that their ideas are bat poop crazy because it's not tempered by reality, ego driven. No, I am by all means. He's a douche canoe, and his ideas are batshit crazy. I am in no way going to say that his idea of what this object is factual in any way whatsoever. I won't even say that it's likely in any way whatsoever. But I will say that it is possible. And I'll get into that in a second. But this here is the basically is a schematic of its path. The white line is the object, and the fuchsia line in the center, that is Mercury in its orbit. The pink line is Venus in its orbit. Blue line is Earth in its orbit. Red is Mars, and then gold is Jupiter. And I don't remember where or when. Let me. Is it this one? Oh, no, that's not that one. No. Okay. No, it doesn't tell me. This schematic is relevant at a specific time. So these dots are not just thrown in there willy-nilly. This represents what the current geometry is at a particular time. What's interesting is there are 2 interesting things about, or there are 2 things that I find to be compelling about this object's orbit. One, it's retrograde, meaning that it is moving clockwise relative to the sun in this viewpoint. Meaning, more specifically, it's moving from the upper right to the lower left. And it's going to reach where Mars is currently on that diagram around late October 29th, I think. The other planets are moving in a prograde manner, meaning that they're rotating or revolving around the sun in a clockwise direction, meaning that they're going. They're moving in a prograde direction, meaning that they're going counterclockwise. So they are going like, yes, like this. I can or perspective, whatever. So the point being is that as you look at this, when Atlas gets to the point of Mars's orbit, it's going to be fairly close to it. And I use the word fairly loosely. I recognize that it is a very subjective term, and again I will touch back on this point again, because there is a lot of the use of the subjective on both sides of this, which is one of the reasons why I'm irritated and why I went live. It's going to get close to Mars. I don't remember how close, but it's going to get within, I don't know. I don't remember how close, but close enough. Close enough to be interesting, I guess. It's also going to get close to Jupiter, because Jupiter is going to move further along in its orbit by the time that Atlas takes to get down this way. So when Atlas is down here, Jupiter is going to have swung over here. So it's going to get fairly close to Jupiter. I think it's also going to get fairly close to something else. I bring this up because Dr. Loeb points these out as, in some way, as pieces of evidence to suggest that this is in fact an interstellar probe, that this is an object whose mission, I suppose, or whose objective includes close flybys of various objects within the solar system. Okay, great. Sure. Complete speculation. The other thing that's compelling about this is that the orbital path of the object, of Atlas, is within the plane of the ecliptic. Now, what is the plane of the ecliptic? The plane of the ecliptic is one way in which you can define the orientation of the solar system. And it is defined simply as the plane through which the Earth passes around the sun. So if you look at the orbit of the Earth around the sun and call that a flat plane, that is the ecliptic. All of the planets, the planets, with the exception of Pluto. Yes, Pluto is a planet. All of the other planets lie within, I think, 10 degrees of the ecliptic. And this is with, I can't remember off the top of my head, I should know this. I think I just read it. Do I have it up? Do I have it open? I think I closed it. Sorry. I was reading through some papers. I had to restart my system. Anyway, squirrel. So I think it's within 15 degrees. I don't know. It would be considered within the plane of the ecliptic if you are a solar system astronomer. I find this compelling because as Dr. Loeb, actually Hilbert was the primary author on this on the paper. He is correct in stating that the probability of this happening is very low, given the assumption that there is no preferential direction for interstellar objects to come within our solar system. If you assume that objects can come in at any angle, any inclination angle from the ecliptic, then the chances of one passing along the ecliptic is very low. That is true. Okay, and so that is one of the reasons why, I think one of the primary motivators for why Hibbert et al., Avi Loeb, so forth, have hung their hat on the fact that this must, in fact, be aliens and some kind of craft of some sort. And so I've heard people sort of debunk this point, and they're like, well, yes, it's a chance alignment, but really, that's nothing it's not notable. I don't like either of these sentiments because of the fact that, let's count them, folks. 1, 2, 3. Interstellar objects have been discovered and analyzed, or have been observed, and their orbits analyzed in any way whatsoever. This is a data sample of 3. You guessed it, 3. In astronomy, a data sample of 3 really doesn't tell you shit. You really cannot say. The only thing that you can really say about these objects, or about this phenomenon, is that A, interstellar objects exist, and yeah, you can also make arguments, which have been made, that these objects should be fairly common. These are based on models of planetary system formation, and that involve ejection statistics, basically gravitational interactions which force things to fly off, and they are no longer gravitationally bound with their star. And given that these 3 objects have been found within the last, I think, 7 years, does point to the idea that these objects could be very common. However, it points in that direction. We as astronomers, if we are being honest, have to say that we have not completely ruled out that these are in fact just chance encounters. That we cannot rule out the fact that we may not see another one of these for decades, if ever. Now, the chances of that, from our current understanding, are low, or our expectation, rather, is that the possibility of that is low. But we have 3 points of data. And as I have harped on many, many times, science is data-driven. So any characterization of whether or not this orbit is peculiar, is intentional, or nothing to really is not notable, any statement to those effect is bullshit. Basically, they are either lying or, and this is the important part, they are trying to sell you something. The people who say that it's preferential, they have a worldview that aliens exist and they are coming to our planet with some kind of regularity, and they are causing this data to fit that narrative. Those who are saying that it's not notable basically understand that Avi Loeb is a douche canoe and they want to dunk on him, which I perfectly get. I perfectly well get. But the problem with that is that, again, we need to be honest if we're going to do it. It is notable that this object is within the plane of the ecliptic. What does that mean? I don't know. No one knows. We need more data. Now, someone had asked, do they know the origin of the object? Is it the Oort cloud or further? That's a question that I have, actually, and I've looked into. Because I thought to myself, could this potentially have been an object within the Oort cloud that experienced a gravitational interaction that was sufficiently high that it swung it into our solar system at what we now believe to be, I think it's 60 kilometers per second. Or I think you'll start seeing numbers like 130,000 miles per hour or something like that. Flat Earthers are going to have a field day with that number. But I think it's around 60 kilometers per second, which is very high. It is the fastest moving object that we have ever discovered in the solar system. It is far faster than Oumuamua. It's far faster than, Borisov? But that, from what little I have found, and again, this has just recently been discovered. This was discovered back in July. I'm actually surprised by the number of papers that I have found on this, where data has been analyzed. Most of them are not. Most of them have not been peer-reviewed yet, but so I'm taking it on faith. Yes, flat earthers, I did say the F word. I'm taking these on faith because they haven't been peer-reviewed, but, you know, it is what it is. All of them basically say that this thing must be interstellar. And the eccentricity of this is 6. As you can see on the screen, that's very close to a straight line. The Oort cloud is theorized to be about, around 100,000 AU out. So that would imply a certain amount of mass. I would think that would imply a certain amount of mass is necessary in order to create that sort of trajectory, to give it that kind of force. And so it would be fairly trivial, I think, to be able to test that hypothesis. You know how fast it's moving. You make the assumption that it didn't really move or hasn't really changed its speed since leaving the Oort cloud, if it came from there. That gives you a time scale. You now can look to see whether or not there was an object that could potentially be responsible for slinging it into the inner solar system. And then out again. As far as I know, no such object exists. But it would be interesting if someone would actually take the time and look into it, instead of just saying, yep, it's interstellar because the orbit is hyperbolic. It has also got some interesting physical characteristics, which I'll get into in a second. Which again prompted Hibbard and Hilbard. I really should know his name. Hillard. I think it's Hillard. I think it's Hillard. Loeb is actually the third author on that paper. Now, another thing that was driving it is the fact that the composition of this object seems to be weird in one way or another. Well, that brings us to the most recent observation, and bloop, there we go. This is from Hubble. Wow, that is really bright on my face. Sorry about the brightness. Can I do this? Oops, let me do that. Yes, you go over here. Stupid monitor controls. I can tech. Go this way. Yes, okay. Better, I guess. Anyway, so yeah, this is a Hubble image that was taken July 21st of this year. It's interesting because I think this is a composite, and what's interesting to me is that this is basically a set of they made 4 observations with this. They made two 20-second exposures and 2 44-second exposures. I don't know if this is a stack of those. I don't think so, because of the fact that they were taken in different parts of the orbit. But it really does actually go to the power of the Hubble telescope. This is an object that has effectively an absolute magnitude of around 17, if I remember correctly. You probably have no idea what that means, but a magnitude of 17 is very, very faint. It is basically the faintness limit of the telescope here, or the 32-inch telescope here here at George Mason. That means that if an object has a magnitude that is higher than that, or the object is dimmer than that, then we can't see it. So yeah, Hubble was able to image this thing using a 22 and a 44-second exposure. It's able to look at stuff in seconds that our 32-inch telescope can't even see, basically. So the Hubble is still a fantastic instrument. And so I wanted to point that out, because this is from an astronomer point of view, from an observational astronomer point of view, this is just fucking amazing. Now, this image basically challenges to a very large extent one of Avi's talking points, which is in the earliest observations, a coma, or rather any sort of tail, any sort of asymmetric coma was not detected. Real brief. A comet can be is said to be composed of three basic parts. The nucleus, and you can think of that as the actual object. That is the physical object that is composed of rock, probably metal, and ice of one variety or another. That is the thing that you have to worry about if it smacks into something. That is the nucleus. Then you have a coma. A coma is an envelope of gas which has stemmed from the nucleus. It originates from the nucleus. And as I said, the object is composed of rock, of metal, and ice. When ice sublimates, basically goes from, because of the pressures involved, water or solid ice does not go to liquid form. It goes immediately to gas. And so it becomes vapor. When it does so, microscopic, basically particles on the order of microns to millimeters, these particles of dirt, sand, or what have you, they get carried out. They get basically expelled away from the comet or the nucleus due to the action of the sublimation. And they will hang around the comet for a while and form this roughly circular, roughly spherical shape. That's the, that's the fuzzy bit. That's the light blue bit that you can see around it. Now, the first observations were, taken when the object was further away. Therefore, it was colder. Therefore, the amount of sublimation was lower. So the coma is going to be smaller. Also, that brings me to the third part of a comet, and that is the thing that makes a comet in everyone's eyes, the tail. So you have this tail of material streaming outward from it. You can actually have two types of tails, but in this case, don't worry about it. We'll just mention tail. And so in the first images, you did not see any indication of a tail. And so, based on its brightness and an assumption about its reflectivity, if it were an asteroid, its size would be huge. It would be extremely large, and I apologize, I do not have a number for you. It would be inordinately large. It would be, in the sense that it would be much, much higher than would be expected of an object of that size to be streaming through here. I'm not entirely certain where they get that assessment, but that is the consensus, is that objects of that size, it would be rare for those objects of that size to be streaming through the solar system. So it would be highly, highly unlikely for it to be an asteroid. At the time, Hillard et al., I'll just say Loeb. I want to give the first author his due, but I can't remember his first name, so I don't know how much due I'm going to give him. Loeb's the colors of the light indicated a certain composition that was not exactly cometary, didn't exactly fit with the comets that we see here in our solar system. So Loeb took that and basically said, all right, it can't be an asteroid because it's too big. It's not a comet because it's not colored correctly. Therefore, aliens. Okay. Well, that is a suspiciously low bar of evidence to conclude that it's got to be aliens. And that paper it goes off on, you know how I have a problem with celestial theodolite, where the initial premise is flawed, so therefore I don't really care about the rest of it? The rest of that paper is, albeit novel, it is basically talking about the likelihood or the chances that we would be able to intercept the alien spacecraft given a certain amount of conditions. I suppose from an engineering standpoint, if I were someone who was a orbital mechanics geek, I'm not. If I were an orbital mechanics geek, then that would interest me in one way or another. But it doesn't. And so I basically skimmed the rest of the paper. But again, one of his pieces of evidence to say that this was not in fact a comet was the lack of any kind of tail, or the development of any kind of tail. As you can clearly see here, there does appear to be some form of tail forming off to the right, and that is anti-solar, meaning that it is not in the direction away from the sun. Now, is it pointing directly away from the sun? It's within, I believe it's within 38 degrees opposite of the sun. So it may not be dead on directly away from the sun. It's in some kind of best guess at this point with the data that we have. It's in a 38 degree arc somewhere in behind it. So there does appear to be some kind of tail. And so, yeah. And when we now have better observations. And yes, it is definitely redder. Do I have... You know what? I should just bring these papers up. I should just open them. That one. What is this one? That would be this one. All right. Does this have the nice... So... This is the NASA preprint that they're talking about. That's not the one I want. Please bear with me. I know you all are just riveted. There's this paper by Taylor and Seligman that irritates me, but it does have a nifty little graph. Or it did. What? No, this isn't the one, apparently. I have a paper that has a nifty little plot. There it is. Let's see if I can do this. Let me add another. Sure. That one. There we go. Awesome. There we go. There we go. This is a paper by... well, there you go. By Bolin et al. Interstellar Comet 3I Atlas, Discovery and Physical Description. It was posted in the monthly notices of the Royal Astronomical Society. It is free. It is refereed. I think this actually was... This is refereed and published. This is free, so you can Google this and get your own copy of it. It's not behind a paywall. And this talks about... Oh, here we go. Asteroid Terrestrial Impact Last Alert System is what ATLAS stands for. It was discovered on July 1st, 2025, and it has been observed by a number of different ground-based observatories in a whole lot of different filters. Basically different colors. B is blue, V is green, R is red, I is really, really, really red. Green is G is a very, very specific shade of green. Little r is a very, very specific shade of red. You get the picture. And so these numbers basically are astronomical speak for what color is it. And what they found is... Why does this not do what I want it to do? So here are some of these early pictures that I was talking about, that Loeb was like, not a comet. And there's no cometary trail or anything like that. He basically said that there was poor tracking involved. Now, again, because I'm that guy, is the image blurred out because of poor tracking? I would imagine there is some the tracking isn't perfect. Because I cannot imagine, given the small amount of observations, that the orbital parameters of this object are known to extremely high precision. So I have to believe that some portion of this blurring is because the tracking rate of the telescopes is not accurate. Now, how much? I don't know, because I don't know what the current orbital elements are or what their errors are. I would imagine that if they were large, then these authors would know that and would say, hey, we are, the blurring could be due to tracking issues. But they don't. So, But again, I'm that guy. I'm giving you my honest perspective on this, is that the tracking rate for this object is probably not known precisely. So there could be error. There are errors in tracking with this object. Albeit they may be very small, but they are there. So anyway, whole point of this is we get to this plot, and this is what we in astronomy like to call a color plot. We have R minus I, which is basically red minus really, 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 really red, in comparison to green minus red. What this is useful for is that from a star point of view, a star of a given temperature is going to have a certain color. It's going to have a certain placement on this diagram. It's going to have a very, very specific red minus really, 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 really red, and a very specific green green minus red position based on its temperature. Here, it's based on its composition. So these are so the big orange dot to the bottom left is the sun. The other little points in there indicate different types of solar system small bodies, trans-Newtonian objects, comets, so forth and so on. What you can see is that the salient point is that as you go to the right, it gets redder. The object gets redder, which indicates has implications to its composition. Specifically, in my understanding, just how much ice there is in relation to how much dirt there is. More specifically, how much metal there is. 3 Alice is the red cross. The yellow cross is Oumuamua, and is it Borislav? We'll call it Borislav. I'm sure I got it wrong. Borislav is purple. What this indicates is that this object is of a comparable color to Oumuamua, although it's even more red from what I'm gathering, and it is way redder than Borisov. But, as may have mentioned before, I don't know if you caught it, I may have mentioned, we have 1, 2, 3, data points. Therefore, we have no idea if any of these or all of these are weird for an interstellar object. Now, from a cometary standpoint, Oumuamua and Atlas are definitely redder than we would see in any object within our own solar system, but that could very well be because of the fact that it is interstellar in origin. It could have been damaged by cosmic ray events in its long travel through the solar, through interstellar space. That could have affected its current color. Another thing to note is that the color is also dependent. What we're looking at is effectively the color of the coma. We're not looking at the color of the nucleus. We're looking at the color of the gas and dust, mainly the gas that is surrounding the rock. That's going to change over time as the comet gets closer to the sun and more sublimation happens. So that is more than likely going to change over time, which is one of the things that's so exciting about this object. And I don't know if it's been talked about, and I'm waiting until an hour into this to talk about it. Is that we only have 3 data points, and the other 2 we never caught them this early. We're going to have months of data on this object from where it's fairly distant from the sun. Right now, it's I think at 3.8 AU. It's going to get, I think its closest approach is around 1.5. But we're going to see this evolve in real time. We're going to be able to watch this comet sublimate, outgas, create a coma. Well, it's already created a coma. Create a tail, and then back again. So we're going to be able to get a tremendous amount of data on an object which more than likely did not originate in this solar system. Which brings me, I don't know if I want, no, I'm not going to get into that yet because this stream is longer, is already an hour long. But this is awesome. The fact that we're seeing this is what gets me fucking excited, is that we are looking at an object that is, one, peculiar from our own solar system, from objects within our own solar system. And we get to see this sucker evolve with time. And we get to see how its color changes. We will start getting better estimates of how big it is, how fast it's moving, things of that nature. I am really, really pumped. Whoops, that's not what I want. Anyway, I'm really, really pumped to see how that, see how this thing goes as we move forward. Where was I? I don't remember. So Avi was saying that it was too red or what have you. As we find out, is that it's not too red. I mean, is it on the extremum of solar system objects? Yes. But it is comparable to Oumuamua, although he does believe that Oumuamua is also an alien spacecraft, so I mean, I guess that would probably strengthen his argument or his resolve. But yeah, but now it's clear that we have this. Now, the next thing I'm going to show you, it's not nearly as exciting because it is a preprint. Basically, this paper has not been reviewed, but this is the Hubble paper that I was talking about. So that image that I put up, this is the paper that accompanies it. That data paper, it's early. I don't know. I'm babbling at this point. Hubble Space Telescope. There we go. All right. Nope. Damn it. Hold on. Trying to resize things, and I'm failing miserably. That one? That one. All right. Fudge. Stupid click. Can he do it? Yes, he can. Awesome. Yay! So yeah, this paper, real boring. No pictures. There's some equations in there if you're into that sort of thing. But, there's not even tables. So, yay. But what I love about this paper is that it's real speculative. It does not, it does not say really, how would I want to put this? One, it acknowledges that we have 3 data points. So you really can't make any solid inferences really about the nature of interstellar objects at all. It also talks about, it says that the crude limit of the nucleus. It realizes that these authors realize that these measurements are only going to give them not approximate figures, but these are not, hard and fast, precise numbers. So they talk about how they do this. Oh, I'm sorry. The absolute magnitude is actually around 14, so it's brighter than that, but its apparent magnitude is 20. So our telescope, the 32-inch telescope, would not be able to see this thing at all. Even with the best sky, not yet. Hubble, 22 seconds. Yeah. Stupid Hubble. And so they go into the morphology and they talk about the methodology behind it, and they basically are able to quantify that, yes, there is a asymmetric coma coming around it, going around this nucleus. They are not able to determine the size of the nucleus. It is far too small given the observations that they have. Basically, the pixel scale is too crude. The pixels are too big, and so there's just not enough light over enough pixels in order to really make any kind of size determination, angular size determination of the nucleus. But they are able to come up with estimates of the coma, and I'm trying to find the best number. When I say best number, what I'm really meaning by this is there are a number of assumptions in this that need to be acknowledged. One, and this is the primary one, is the reflectivity. They are assuming an albedo of 0.04 for this object, and they don't explain where that comes from. I'm assuming that's because the comet folks have a justifiable reason for why the reflectivity of this object, or the albedo is basically 0.4%, something like that. I think I got that right. Discussion. Let's get to the main points. So, they determined that due to the brightness profile, the nucleus cannot be larger than 2.8 kilometers. So the best they were able to do was determine an upper limit. They know that the nucleus is no larger than 2.8 kilometers. They make an argument to suggest that the nucleus is probably sub-kilometer in size. The coma itself, I think, I see the number 60. It's on the order of tens of kilometers across, I believe. You know what? Let me find it. I don't want to throw out numbers. Morphology. Plume, preferential, along the position angle of 280. So 280 degrees, basically anti-solar. Surface brightness profile. So some of the other assumptions that are in this is that we don't know what the material is exactly composed of yet. We don't have, at least for these authors, they don't have good spectroscopic data or reliable spectroscopic data in order to identify what the coma is actually composed of. If it is cometary, it is most likely composed of OH gas, carbon monoxide, or water vapor. Because of the sizes of those, the properties of those molecules, that is going to affect things like how big it is and its mass loss rate. So this is talking about the velocity of the material being thrown out. This is an argument for that the particles are actually large in nature. I know that there's, maybe it's in the abstract. I know that there is... Oh no, they actually don't talk about... So I'm sorry, yeah, they basically, the nucleus is somewhere in their estimation between 2.8 kilometers all the way down to 0.16 kilometers. So it cannot be any smaller than 0.16 kilometers if it is, if the gas is composed of, or the ice rather, is composed of carbon monoxide. It would be bigger, that bottom limit would be bigger, I believe, if the ice were made up of OH or water. It also has to do with other assumptions, and I apologize if this is making you ill, such as the mass loss rate and so forth. It makes assumptions as to the grain size. How big are the dust grains that are coming off of this thing? But here are the, let me just finish off by talking about the highlights of this paper, of the observations that they made and their analysis. And like I said, they were very cautious in how they describe these things. They were very cautious to say that this is very preliminary. We do not have enough data to make really, really firm claims about these basic characteristics. These are the characteristics that we can hang our hat on, as it were, at this point, given this data. And so again, because of the brightness profile, the comet, the nucleus cannot be any larger than 2.8 kilometers in size. There so far does not appear to be a tail, an actual physical tail. The coma is asymmetric, so there is sort of this teardrop shape to it, but the actual a formed tail does not appear to be. A tail has not appeared to have formed yet. What's interesting about this also is, and I'm not going to get too far in the weeds with it, but there is also something rather peculiar that, again, is very, very tentative at this point. There is a solar coma, as it were. There does appear to be gas that is being released towards the sun, and it's asymmetric. This is not unexpected because, again, the ice, the depth of the ice around the nucleus is not going to be homogeneous. It's not going to be a constant thickness. Some of it is going to be thinner than others, and so therefore the sublimation is going to be larger in some areas than others, or at least the release of the gas is going to be larger in some areas than others. So this is not unexpected. What is sort of unexpected is the characteristics of this seem to indicate the possibility that, again, and this is interesting. I won't say anything more about it, or I won't try to put a reason behind it. But all things in the universe rotate. Everything does. And so a comet going through the solar system, going through interstellar, is going to have some kind of coherent spin. What the data is suggesting at this point is that spin is actually, the rotation axis is actually pointed at the sun or along the solar direction in some way. Not, again, not precisely at the sun, but in line with it. Which again is weird, because we don't expect that spin axis would have a preferential direction. So the fact that it is spinning such that one hemisphere of the comet is constantly getting irradiated, that there is no day-night to this thing, or the surface does not experience day and night. It just simply experiences one hemisphere is hot, the other hemisphere is not. One hemisphere has a high rate of sublimation, the other hemisphere doesn't. And so that is peculiar. And you know, I find that to be compelling. They talk about the mass loss rates. The mass loss rate is anywhere between 6 to 60 kilograms per second. They make a note in the paper to say that this is a negligible amount of the total mass of the comet. So if you hear anyone, and I just watched a video on it, they presented the idea that this comet could be destroyed, that it basically could be eradicated by the sun. That is highly unlikely. It is not going to sublimate itself to bits. It is not going to be hot enough to do it. It's not going to lose enough mass to do that. And it is not going to get anywhere close to a large enough gravitational body for it to be ripped apart. It is getting close to Mars, but not nearly that, not close enough. It's going to get close to Jupiter, but not close enough, at least as far as we know at the present time. So if you hear anyone tell you that this object may in fact get destroyed while it's within the solar system, that is highly unlikely, based on what we're seeing here. I'm sorry. The three ices are carbon monoxide, carbon dioxide, and water vapor. And so, yeah, that's basically it. I just kind of wanted to share that with you. Hopefully that wasn't exceedingly boring. Oh, hey, I turned myself off. That's not good. Let me go over here. And so, howdy, Nico. So yes, let's recap. Based on the Hubble observations that we currently have, that were taken on July 25th, the likelihood that this is a comet has greatly increased. We now see cometary features on it. Its colors, while on the redder end of what is seen within our solar system, are not inconsistent with that. So any argument based on the color of Atlas pointing towards an extraterrestrial object, or excuse me, pointing towards an alien, is specious at best. It has a color similar-ish to Oumuamua, which again, if you think that that's a spacecraft, I guess that argument really isn't all that compelling. But really, yes. So really, these observations are supplying pretty solid evidence that this is in fact not a comet, or not. This is in fact not an alien spacecraft. Later, I'm going to do a video where I talk about where lobe is most problematic, and this is in line with what I've talked about in the past, which is that science needs to be unbiased, that science needs to be objective, that effectively, while it is inescapable for us as human beings we have a worldview, it is inescapable to, I was trying to say this in a concise, punchy way, but it is not possible for us to escape having a worldview about the world around us. as a scientist, it is of vital importance that we understand we have these worldviews and that we do not allow these worldviews to dictate our interpretation of data. Science is data driven. We go where the science tells us. We do not force the science, or we do not force the data to follow our worldview. And so this is one of the two things that is most egregious in terms of Avi Loeb, in my opinion, is that as a scientist, he should know better. His worldview is that aliens not only exist, they are intelligent, they are capable of building spacecraft, and they are capable of traveling interstellar space, and that they are coming to us. That is a lot of facts that are not in evidence. So the fact that he is so adamant that this is extra evidence of extraterrestrial intelligence, even though in the paper that I've been referring to, they do say that it is speculative, but they do put it forward as a viable option, and not simply just, hey, this is interesting speculation. Hey, maybe it could be aliens. No, they are pretty upfront in saying that this is a viable explanation for why this is this object, or what this object is. That is not how science is done. That is not how science should be done. And that sort of bullshit leads to a lack of faith within the public. Because if we were to go out there and say, oh yeah, this is definitely extraterrestrial intelligence, these are definitely aliens, and as the data is now telling us, or indicating, that as this thing gets closer and actually starts, the gas starts sublimating, it's going to look more and more cometary. The public is going to be like, well, wait a minute, you said it was a comet, or you said it was aliens. Now you're saying it's a comet? What am I supposed to trust? So we cannot be making these statements. We cannot be making these extraordinary claims without extraordinary evidence. And more specifically, we need to not be making claims about the physical nature of things that are clearly coming from a worldview, coming from something, an opinion or a viewpoint that is not supported as of yet by evidence. So I will leave it at that. Howdy, Nimrod. And so I will leave it at that. The stream is now, I've been going for hour and a half. So yeah, longer than I intended. So I hope you, for those of you who are watching now, I hope you go back and rewatch it. Just as a recap, I talked about my thoughts. Basically, I gave my final thoughts on the celestial Theodolite business, and I then went on talking about 31 Atlas. So this is me, Professor Parks, an advocate for the advancement of astronomy. If you like this sort of content, please like, share, subscribe, do all the YouTube-y things. If you'd like to support me or support the observatory, please consider sending me some of that yummy cash via PayPal. That money goes directly back into the observatory, into observatory improvements. If you'd like to help me out financially, please consider becoming a channel member. I will be posting more videos that are basically behind the scenes looks at what's going on at the observatory and what is going on with the Landalt mission that the observatory is a part of. So that being said, how am I, Nimrod? Well, I started the stream off by saying I'm bored and irritated. I'm no longer bored, and I'm less irritated, but I'm managing. Hope you're doing well. All right. Peace out and clear skies.